Okay. Yeah, please just feel free to jump in if you have a question. All right. So NiMARE, which stands for Neuroimaging Meta-analysis Research Environment, is a Python library for performing neuroimaging meta-analyses as well as related analyses like functional decoding, automated annotation, searching through large-scale meta-analytic data sets like Neurosynth or NeuroQuery, and a few other things. The goal with NiMARE is to take what is currently a bunch of different implementations of different algorithms for meta-analyses and consolidate them into one place, provide a standardized interface, and allow people to basically use whatever tool is most appropriate for a given research question, rather than the tools that they are most familiar with. So there are a number of tools that you all may be familiar with for meta-analysis, including BrainMap, which is a large coordinate-based database that is manually annotated and can be searched with one tool called Sleuth, can be added to with another tool called Scribe, and can have meta-analyses performed on it with a third tool called Ginger Ale. Neurosynth is another very popular tool. It's a database of automatically extracted coordinates and annotations from the literature, and a web interface and Python library for performing meta-analyses and functional decoding on that specific automated database. A third underutilized tool is NeuroVault, which is a web interface for storing and sharing statistical images, which can be really useful for image-based meta-analysis as well as functional decoding. And then there are a few other coordinate-based meta-analysis tools, such as seed-based demapping and the MATLAB MKDA toolbox, that are used primarily in different areas within the field. So many of these tools are either closed source or primarily developed with a graphical user interface in mind, or written in a programming language that most neuroimagers don't know, like Java or C++. On top of that, there are a bunch of tools, or algorithms, I should say, out there being developed every year and being published in papers without a well-documented or well-tested implementation available. So in NiMARE, what we try to do is we try to implement each of these algorithms, provide methods for interacting with these different databases, and then provide an avenue in which people who develop new algorithms can share them with the community. NiMARE is primarily designed to be similar to scikit-learn, which if you're in this tutorial, you are probably familiar with. What that means is it's an object-oriented approach wherein you initialize classes with a number of parameters, and then you can apply certain methods from those classes to take in data and produce a different output. So after initialization, the initialized object can then be fitted in many cases, such as for meta-analytic estimators, which is just the meta-analysis tools, can be fitted to a dataset object and produce a meta-result object, which contains statistical maps and additional information about the meta-analysis. There are also transformer classes, which implement a transform method, which can take in sometimes a data set and produce another data set, or take in a result and produce another result.
Hey, Taylor, would you mind making the text on your screen a little bigger? Or it's a little hard for us to see here in person.
Yes. Is that readable?
That's great. Yeah, thank you.
All right, perfect. So yeah, these transformer classes take in one version of an object and produce a new version of the same type of object. NiMARE is currently, we just released version 0.0.12, where we're getting very close to a 0.1.0, so a minor release. What that means is that it's in alpha development, and we would love feedback, we'd love bug reports, but it also means that the actual interface can change in the future. We monitor Neurostars with the NiMARE tag, and then we also monitor the issues tracker on the GitHub repository. So for this tutorial, I wanted to cover a few different topics, including compiling meta-analytic datasets, working with meta-analytic datasets, searching large databases like Neurosynth or NeuroQuery, performing coordinate-based meta-analysis, performing image-based meta-analysis, and then performing functional decoding. And in this case, we'll specifically use Neurosynth. And JB did mention in the Slack that other tools that are important and that I haven't updated this tutorial to include one other tool is NeuroQuery. NeuroQuery is another automated database like, well, it's a database like Neurosynth, but it's also a tool for performing sort of meta-analyses from, it's an encoding tool that can predict statistical maps from text or labels. And NiMARE includes methods for ingesting NeuroQuery's database so that you can actually perform meta-analyses using NeuroQuery, just like with Neurosynth. All right. So we'll start off with some imports. Most things are available at the top level for NiMARE, so you don't typically have to do from blank import or from NiMARE import a given submodule. All right. And all the data are located in this Jovian shared meta-analysis folder. Now, there are, as I've mentioned, different tools out there that have different organizational structures for their data. NiMARE has been primarily relying on a specification that we, as a community, have developed called NiMADS. There's a link to the NiMADS documentation if you'd like to take a look. What it is a standard for organizing meta-analytic datasets as JSON files. These datasets can include peak coordinates, statistical images, metadata, annotations, raw text, and certain other information. Now, it's pretty complicated structure. So most NiMARE users don't actually create these JSON files by hand. What they do is they will typically take in format or use formats that are more common, like Neurosynth or Sleuth. And then NiMARE will convert those tools or those files to the NiMADS format. The three formats that we currently cover, although we would love to cover more, are the BrainMap Sleuth tools text files, Neurosynth and NeuroQuery database files, and of course NiMADS JSON files. So Sleuth files are files outputted by BrainMap Sleuth app, which lets you search the BrainMap database and select studies and then output the coordinates for those studies in a specific format. And then GingerAle, which is BrainMap's meta-analysis tool, can ingest Sleuth files and perform ALE meta-analyses on those files. Here's an example file from a 2015 paper on phase paradigms. The contents look sort of like this. All of the coordinates need to be in one space, either TallyRack or MNI. And then after that, you have the study name or study identifier, as well as a specific contrast identifier, as well as, in addition to that, we have a sample size underneath. And then we have a range of coordinates from that contrast, followed by the next study, and so on. And NiMARE has a tool to convert this Sleuth file to a data set. And the data set contains 386 experiments. And we have the space set as the AL 2mm MNI template. In addition to sleuth files, we also support Neurosynth and NeuroQuery databases. So you can fetch these from the actual dataset files are located on GitHub in different repositories. NiMARE has functions to extract or download those files, which I'm not going to run because we can't create new files, and it would also take quite a long time to do this. There's also a function to convert these files to a data set. And what I did here is I downloaded the files. I selected version 7 of Neurosynth, as well as annotations from the abstracts. In this case, these were TF-IDF weights. So these were just terms extracted from the abstracts and then converted into term frequency inverse document frequency values. Those are selected, downloaded, and converted to a data set right here. And then I took the first 500 studies for this tutorial using the dataset object slice method, which allows you to feed in a subset of the IDs in the dataset to produce a reduced version of that dataset. And then I saved that to a gzip pickle file. So that pickle file is located here. I'm just going to load it with the dataset objects class method .load. So this one contains 500 experiments in MNI 152 2x2 space. Next, we have NIMAD's JSON files. We have one manually curated data set or file in NIMAD's format that is based on collection 1425 on NeuroVault, which is a set of NIDM results packs for 21 pain studies. So these have coordinates and statistical maps for a number of pain studies. Here's what the contents of that file look like, the first 80 lines. So we have the study identifier. Then we get into a list of the contrasts. The first contrast, which we imaginatively labeled 1, has coordinates in MNI space. These are a list of the X coordinates, the Y coordinates, and the Z coordinates, followed by relative paths to images, statistical images. In this case, we have parameter estimates, error standard variance of the parameter estimates, t-values, and we don't have z-values for this one. And then we have certain metadata for the contrast, which includes the list of any sample sizes associated with that contrast. Then it goes on to additional studies in the data set. So what we can do is we can directly initialize a dataset object with this NIMADS file, which produces a dataset. Now, we also have a function specifically to download this NIDM pain dataset to a specific folder. So that means all of the statistical images for the dataset, because the dataset file really only contains relative paths to those images. And then we have to update the path. So this essentially just points to where those images are located on the local machine so that the data set can actually access the statistical maps. All right. I actually could print the data set itself, which has 21 experiments in MNI 152 space. Now, the dataset object, which I've been referencing quite a lot, is the basic object from NiMARE. What it does is it contains all the relevant information that's stored in the NIMADS object or the NIMADS file in a in-memory object. There are a number of key attributes to this object, including the identifiers for all the studies in the object. So in this case, since it's the pain data set, we have each of the study IDs, and then a hyphen, and then each of the contrast IDs. in case there's more than one contrast within each study. The majority of the information in this data set is stored in pandas data frames, which stores tabular data like a spreadsheet. The 5 attributes of interest there are .metadata, .coordinates, .images, .annotations, and .texts. Each of them has columns for each of the identifier types. So we have one column for IDs, which is combined study ID and contrast ID. One column for just the study ID, one column for just the contrast ID. And then for coordinates, we also have X, Y, and Z columns, as well as the space of those coordinates. With metadata, the main metadata field that we have been using is the list of sample sizes for a given analysis, because a number of both coordinate and image-based methods use sample size as part of the estimation process. And then there's the images data frame, which has one column for each of the statistical map types. In this case, we have beta, standard error, T, and Z, as well as relative paths to each of them. So these 4 relative columns existed when the data set was initialized. And then the update path method defined where the actual files were located, both in terms of the relative path and in terms of where they are locally. Now, the annotations data frame would contain terms or manual annotations, terms extracted from text, etc. And since this data set doesn't contain any information about annotations, we can look at the Neurosynth data set, which has a lot of annotations. Each of these is a term extracted from the abstract and converted to a TF-IDF value. So the type of annotation is defined in this first part, and then 2 underscores separate it from the actual label. So if we look over here, we can see this is a TF-IDF term from the abstract, and the term itself is yielded. And then each of these values would be a TF-IDF value. In this case, they're all zeros because in these first 5 studies, they didn't use the term yielded. Unfortunately, none of the data sets that I have for the example for this tutorial have text, but we can also include text from the studies, like abstracts are typically what one would probably want to use. But you could also have full text, you can have different sections, whatever you can extract. So in addition to these attributes, we also have a masker attribute and a space attribute. The masker is a NiLearn masker object, which defines how coordinates or how images are switched between NumPy arrays and image objects. We also have a space attribute that it's just a string defining the space and resolution in which the data within this data set is stored. Now, data sets can be loaded from pickle.gz files, but they can also be, they can be saved to pickle.gz files and loaded from them. In this case, this is how you would save to a file called paindataset.pkl.gz, which we can't do because we don't have write permissions. All right. So 2 common cases are a manually curated data set that you perform meta-analyses on, or downloading a large-scale data set and then searching that data set for a subset of studies that match your criteria and then performing meta-analyses on that. When you're doing the latter in NiMARE, you're typically using Neurosynth or NeuroQuery dataset or databases. The dataset class contains a number of methods for selecting studies based on certain search criteria. We'll start off with this neurosynth data set, and we will search for specific terms in the annotations data frame. What we use is the get studies by label method. We select studies that have the term pain with a TF-IDF value greater than or equal to 0.001. Then with this list of studies, we can slice the data set to create a reduced version of neurosynth that only contains studies that mention the word pain in the abstract. In this case, because we're working off of only the first 500 studies in neurosynth, there are only 14 experiments, so 14 studies that use the word pain in the abstract. And this will become our data set for decoding, for meta-analysis, what have you. Another common criterion for searching is by coordinates or by mask. So this leads into a specific kind of meta-analysis called a Meta-analytic Co-activation or connectivity modeling analysis called the MACM. And how this works is you search a large database for studies that report at least one coordinate, either in a specific mask or near another coordinate. We have two methods in the dataset object for this. We have get studies by coordinate or get studies by mask. In this case, we're going to use get studies by coordinate to identify any studies that report at least one coordinate within 6 millimeters of this location, 24, -2, -20. This could be multiple coordinates as well, in which case it would identify any studies that report at least one coordinate within 6 millimeters of any of those coordinates. We get a list of IDs from that, and then slice the data set to produce a reduced one. And if we take a look, we can see that there are only 11 experiments that report coordinates within range of this one. So either we've loaded our manually curated data set, or we have searched a large scale database for specific criteria and produced the data set that we want to meta-analyze. So from there, we can actually start performing meta-analyses. The two types of meta-analyses that we support in NiMARE are coordinate-based meta-analyses, which are the most common type, and image-based meta-analyses. NiMARE has a range of different coordinate-based meta-analysis methods, including activation likelihood estimation, multi-level kernel density analysis, both the chi-squared variant and the density version, and specific co-activation likelihood estimation. How these all work is you initialize an object with certain parameters, this object being an estimator. You initialize it with certain parameters, and then you fit that object to a data set. Now, some of the parameters are, for the most part, you can use the defaults for these parameters. Some allow us to really play with the different algorithms, like we can initialize a AL estimator with a different kind of kernel. Kernels being sort of how coordinates are turned into statistical maps that can be analyzed with the coordinate-based method. So the default is always going to be the best kernel for each estimator. So you don't generally have to worry about that. Now, once we've initialized the object and fitted it to the data set, we have our result object. This is what we call a meta result. This meta result primarily contains statistical maps produced by the estimator, which starts off typically with just a statistic. In this case, because this is an AL meta-analysis, these are AL values, as well as p-values and z-values. We can search those, or we can load the image from the object with get map, and then identify the image we care about. In this case, we're going to look at z, and this has the optional parameter return type with the default value of image. This produces a nifty image that's a NiBabble image that can then be plotted or save to a file or what have you. So this is what the statistic looks like, or the statistical map looks like after just an AL meta-analysis. But if you were actually doing this for a paper, this would not be all you want to do. This is just an AL meta-analysis, which has uncorrected Z statistics. If you wanted to actually produce this for a paper, what you'd want to do is multiple comparisons correction as well. NiMARE, so in tools like Ginger Ale and I believe SDM, the multiple comparisons correction is kind of done as part of the meta-analysis, but in NiMARE, we've dissociated it so that you can use a corrector class on a meta-result object in order to produce corrective results. And this lets you swap out different correction methods or not run correction at all, or apply your own correction if you wanted to hack in your own method. What we have implemented in NiMARE is FWE correctors, which correct for or control family-wise error rate, and FDR correctors, which control false discovery rate. In both cases, the corrector is initialized with a method that you say what kind of correction you want to do. And then once that's initialized, you then transform your meta-result object to produce a corrected meta-result object. Each of the correctors implement a range of sort of basic correction methods. So for FWE, for example, you might have Bonferroni correction. For FDR, you might have Benjamini-Hochberg correction. But there are also algorithm-specific correction methods, such as the Monte Carlo method that most coordinate-based meta-analytic algorithms support. This is equivalent to the Monte Carlo procedure that, say, Ginger Ale uses for its multiple comparisons correction. For this tutorial, we're going to just use an FWE correction using the Monte Carlo method, because that's the recommended method. We're only going to do 50 iterations instead of the typical about 10,000 you do for a publication quality meta-analysis. And we're going to use one core. And I'll run that. That takes, it's going to take 35 or so seconds. So I see someone posted something in Slack. I'll take a look at that. The question is, so in the previous example of a coordinate-based meta-analysis, we don't care what the contrasts are when we download the data. We do. So if you're doing a manual meta-analysis, meaning you went on PubMed or you went using Sleuth to actually perform or to identify the studies and then perform the meta-analysis on those studies, you are going to care about what the contrasts are. You want to have contrasts that are compatible and can be synthesized across to test the hypothesis that you have developed. The assumption with large-scale meta-analyses, so with Neurosynth, and the authors of Neurosynth's, the people who created Neurosynth would consider this caveat to be a sort of hand-wavy sort of thing, is the assumption is that when you select studies based on, or when you extract studies based on just the text and grab any coordinates regardless of the contrast, which is how Neurosynth and NeuroQuery are both, I believe, extracted. And then you select based on terms in the abstract or terms in the full text of the paper, you're going to get a fair amount of noise, but the signal will trump the noise. So the idea is that if you select studies that mention pain in an abstract in the Neurosynth database, you're going to get enough studies more than you would for pain studies in, say, Ginger or in the BrainMap database, that the signal from those studies, the coordinates that, or the consistency across those studies will produce a meaningful meta-analysis. In a perfect world, we would be able to search across the whole literature accurately based on different labels or annotations and the contrasts, and then perform meta-analyses on that, on an accurate but large data set. I hope that answers your question. All right, so we have multiple comparisons corrected meta result object, which is a dictionary of arrays. And the available maps now are not just the stat P and Z maps, but we also have voxel level FWE corrected maps, as well as cluster level FWE corrected maps based on both cluster size and cluster mass. And we'll take a look at the cluster size based FWE corrected map produced, the Z statistic map specifically. And this is what it gives us. So if we compare this corrected map, scroll up to show the uncorrected map from before, probably should have shown them side by side. You'll see both that this has far reduced clusters, and that those clusters are singularly valued. So with this cluster level correction, each cluster has a statistical significance rather than each voxel. If we were to look at the voxel level corrected maps, we would see that the individual voxels have their own Z values. All right, and when you've performed the meta-analysis, you typically want to actually look at the results, not just in a figure, but you want to summarize those results in a table of peak coordinates. So we can use NiLearn's reporting modules get clusters table to do that. And that produces a list of clusters with the centers of mass, in this case, or peaks if it's voxel level correction, the statistic associated with that cluster, and the cluster size in millimeters cubed. There's another question. Do you have any recommendations on how to identify if something would be a suitable data set to analyze with NiMARE? In other words, you see a data set online and you think it might answer the question you're trying to ask with your meta-analysis. Is there anything you should look for or look out for when preliminarily exploring the data? So that's a high-level question. So if you have a study, if you're identifying a study to include in a meta-analysis, an individual contrast from a paper, it's worth considering the quality of the study by looking at feature. I mean, with something like AL, it actually weights based on the sample size directly. So you can include low sample size studies and it will account for that. You can also look at the quality of assessing the quality of the methods and the conclusions is always important. Looking at the task itself and the contrast to identify if it fits within your criteria for your meta-analysis is important. Now, in terms of like full data sets, like meta-analytic data sets that you stumble across online, I don't know that that's a very common issue because there aren't a lot of meta-analytic neuroimaging meta-analysis data sets floating around. But it's always worth going back to the individual studies that those data sets are composed of and then reviewing those studies. In NiMARE, we're developing a number of diagnostics as well. So we're working on, say, funnel plots or Galbraith plots, which are very hard to extend to coordinate-based data or image-based data sets. So we don't really have the same means of diagnostics, but the developers, we are trying to work on that. I hope that helps. Speaking of diagnostics, NiMARE also has diagnostic tools for characterizing results. So this will look at both of these tools, look at the clusters from the meta-analysis and try to identify which studies contribute to them. So if we look here, we have 7 clusters from this one. This is a focus counter, by the way. So this focus counter diagnostic, what it does is it just convolves each coordinate from each study with the kernel that was used for the meta-analysis and identifies which clusters that the convolved version of the study has non-zero values in. So basically, which clusters does each study contribute to? And so in this table, we have 0 if it didn't contribute at all, 1 if one coordinate from the study contributed to that cluster, and 2, 3, 4, et cetera, for however many foci peaks from the study contributed to the cluster. The jackknife analysis is a little bit more complicated, and it takes a lot longer. What it does is it runs a series of jackknife versions of the meta-analysis, dropping each study. So what it will do is it'll run, say there are 21 studies in this data set, it will drop the first study, perform the meta-analysis, and then identify the mean value from the cluster, the mean statistic value, and see how that compares to the mean statistic value from the full data set meta-analysis. It then goes to the next study, the next study, the next study, et cetera, to get through all of the studies and produces a table. Let's see, there we go. Produces a table where, just like with the focus counter, each row is one of the studies, and then each value is the percentage, well, not percentage, but fraction, that it would be reduced if that study was removed from the meta-analysis. So higher values indicate that that study had more of an impact on a given cluster. All right. So those are the common steps for coordinate-based meta-analysis. And now we can move on to image-based meta-analysis, unless anyone has any other questions about coordinate-based meta-analyses in NiMARE, or just generally. All right, so with image-based meta-analysis, we're working off of local copies of statistical maps, which are then referenced in this images data frame. So one thing I want to note here is these first 10 studies have T maps, SE maps, and beta maps, but they don't have Z maps, whereas the last 20 or last 11 or so studies all have Z maps. NiMARE has a transforms module. Oh, Arthur has a question. Do you intend to extend the use of NiMARE to structural MRI as well? So at least in the case of the activation likelihood estimation method, the same algorithm is used for voxel-based morphometry VBM as for statistical or fMRI results. So in fact, it's really just a matter of applying it to structural data, as long as those data are VBM peak coordinates. The same probably holds true for the other coordinate-based meta-analysis methods, meaning if you have a data set of VBM coordinates, locations of significant VBM differences between groups, then you can definitely just apply any of the NiMARE methods to those. I am not entirely sure, but I'm reasonably confident that the image-based meta-analysis methods can be applied to VBM results as well, if you have the statistical maps for those. I can't say I have thought about other structural MRI or say diffusion types of meta-analyses. I think we would need input from an expert on those types of data in order to see how to meta-analyze them. All right, so NiMARE has this transforms module, which has a class called an image transformer. And what that can do is that can take in images that are within a data set, and if as long as there's the correct images and metadata are available, it can produce transformed versions of those images. So for example, we have t-statistic maps for the first 10 studies as well as sample size information. And what we want is z-statistic maps if we want to do a meta-analysis that relies on z-statistic maps. So what we do is we initialize this image transformer object. We say which images we want to produce, which are going to be z-maps for a z-statistic meta-analysis, as well as varcope maps, which are the contrast variance images that FSL refers to as varcopes, because we also want to perform a meta-analysis with that uses both beta maps and varcope maps. And we then, once this is initialized, we can apply it to the data set itself with a transform. This produces a new version of the data set. Even though overwrite is off and these images already exist, it takes a moment to do it, to load them, identify them, etc. These warnings right here are from NiLearn, and they're entirely because in the NIDM dataset, the maps that we have not a number of nans outside of the brain rather than zeros. So this kind of upsets NiLearn. However, they're already in M&I space, and they can be resampled into the same resolution stuff without much issue, despite the warnings. So now, if we scroll over to the right, we can see that there are Z maps for these first, it goes down, the first 10 studies, in addition to the existing Z maps from the previous, from the remaining 11 studies that we already had. And if we scroll further right, we can see a new column called varcope and another one called varcope relative that has the varcope maps that we want for the meta-analyses that use both beta maps and varcopes. So in this case, this data set's finely curated, so it was actually trivial to produce these maps. In some cases, some of these maps just won't be generatable. We won't be able to generate them, in which case the meta-analysis will just drop those studies automatically. So one image-based meta-analysis method is Dersimonian layered. We have to set resample to true so that it will produce the images in the right resolution. We initialize the object, we fit it to the data set, and we get a meta results object. We get the same warnings regarding resampling from NiLearn, but these are not a big deal. And then we can get a statistic map. So let me go. So these, I'm looking directly at the dictionary of statistic maps that are produced by the meta-analysis in the meta result object. And with this, we get ZMap, a ZMap, a PMap, an est map. So that's sort of like the stat map. It's the parameter estimate of the mean analysis that was done, a standard error map, and a tau squared map, which is an estimate of between study variance. These have nans around the edges because there's differential coverage between the studies, and not all studies covered all of the brain mask. So that filled it in with not a numbers, and it kept that in these arrays. All right. So we plot the statistical map, where we care in this case about ZMap, and we can see this is something akin to, well, this is the meta-analysis of those beta and varcope maps across these 21 studies. Another method that we wrap around is the Permuted OLS method, which is actually implemented in NiLearn via its Permuted OLS function. So the main benefit of using it in NiMARE is just if you have a NiMARE dataset object. Otherwise, it's probably easier just to use it in NiLearn. But we can We can initialize this. We can fit it, etc. And we can look at the result. So this is just the OLS performed on the beta maps. And then we can also perform multiple comparisons correction using the Monte Carlo method. So that's what NiLearn does with its permuted OLS. We can produce multiple comparison corrected images from that. And it will take a second. And then we can take a look at the resulting maps. It's taking a bit longer than it takes locally. Are there any other, oh, Arthur, did I answer your question sufficiently regarding structural MRI?
Yes.
Yeah, okay. Well, if there are any other questions, given the pause, that would be a good chance to ask them. The steps, so Carolyn asks, I'm wondering if you can speak more to the steps before this tutorial. So in this tutorial, we're analyzing a data set that included many studies. Could you talk about the methodology of prepping data for analysis when the studies aren't already prepackaged together? So for image-based meta-analysis, I'll be honest, we have issues open on NiMARE side for improving documentation of, or improving documentation on building image-based meta-analysis data sets from scratch. Essentially, what you'd want to do in that case is, well, in practice, I believe most people go around emailing the authors of the original papers. And then, or also searching NeuroVault, which contains statistical maps for papers or for maps that match their criteria. And then you would probably want to download those maps and write a JSON file, a NIMADS JSON file matching our format, pointing to those maps. For a coordinate-based database, I will talk about it a little bit at the end. We are working, a number of labs are working together on a tool called Neurosynth Compose as part of the Neurostore toolkit. I'll browse the website in a minute or at the end. What it is it's a sort of hybrid between something like Neurosynth with automatically generated or extracted images, images and coordinates from databases, as well as the ability to manually annotate and curate those data sets. At the moment, though, until that tool is well developed, I think most people would either want to search brain map using the sleuth tool, or manually search something like PubMed and then write those, write the coordinates in a format like sleuth, and then use that to convert into a NiMARE data set, rather than having to work with the NIMADS JSON format directly, because it's a little bit difficult to work with directly. Or, you know, in many cases, searching Neurosynth or NeuroQuery using the tools I've outlined, that's also a strong possibility, and that allows for certain large scale meta-analyses. For example, if you wanted to do meta-analytic independent components analysis or meta-analytic clustering, or large numbers of functional decoding analyses.
Taylor, I have a question.
Oh, yeah.
Is there a way to intelligently guess the n iters parameter for my data?
The number of iterations that were run?
Right. I mean, is there a way to intelligently guess it? I mean, can we tell that if choosing a lower number would lead to faster convergence?
Oh, I see. So I see what you mean. It would be nice to have some sort of minimization step, or look at the fit or the stabilization of the cluster sizes, etc., that are identified by this method. and then stop early. We don't have anything like that implemented. We could probably look at, so we're looking at a few different metrics in the Monte Carlo permutations for at least coordinate-based meta-analyses. We're looking at voxel values for the voxel level correction, cluster sizes, and cluster masses. So if we took all three into account and identified when they stabilize for an early stopping criterion, yeah, that would be lovely and should be implementable, but we haven't done it. Certainly worth opening an issue for, though. In terms of the permuted OLS, though, for image-based meta-analysis, that would have to be, because this light only just wraps around NiLearn, that would actually have to be addressed on NiLearn side. And I don't know that there is a way to do that, or a way to stop early using that procedure. Is that does that answer your question?
Okay, so I would have to implement this outside of NiMARE library. Is that what you mean?
I mean, I think it could be direct. Well, wait, for coordinate-based meta-analyses or image-based meta-analyses?
For taking the three factors into consideration.
Oh, I mean, we would be open to a pull request directly to NiMARE, if there's a solid method for identifying a early stopping criterion.
Okay, thank you.
Yeah, thank you. That's a great idea. All right, so right, the permuted OLS results. What we have from the original meta-analysis was T and Z values, and then when we did multiple comparisons correction, we also got voxel level corrected maps. Recently, I also implemented cluster level correction in permuted OLS in NiLearn. So in the next release, 0.9.2 or so, that will be available as well, as long as you have that installed and ready when you run a image-based or a permuted OLS method meta-analysis in NiMARE. So as you can see, compared to the uncorrected results, these are much reduced and more specific. We can also get the cluster table from this. In this case, we only have 2 clusters, but we get the locations of those clusters. We get the, I mean, this is using a specific stat threshold and cluster threshold, not the same as what's up here, because this obviously has much more clusters shown. So yeah, we can run get cluster table, and here we can compare the 2 results. In this case, permuted OLS, we only ran 1,000 iterations. We would want to run probably 10,000 for an actual analysis. We don't get much, if any, significant results. There's 1 voxel up here that shows up. And for the coordinate-based method, again, we only use 50 iterations. We should use 10,000 or so when we want to run the meta-analysis for a publishable study. We get substantially more results, but yeah, those are just limitations of the tutorial primarily. All right, in the next section, I'm going to talk about functional decoding, which is something that it's a pretty cool application of meta-analytic data. What it refers to is methods which attempt to infer mental processes, tasks, etc., from imaging data. There are a bunch of different ways to do this. For example, using images directly, which many people have published in the past, but one set of approaches uses meta-analytic databases like Neurostore or BrainMap. And we call this meta-analytic functional decoding to reduce confusion between the different methods. There's a good overview of functional decoding in general in this PullDrag paper that I have linked, but I'm just going to talk about the versions that we have implemented in NiMARE at the moment. Specifically, we have 3 different general types of functional decoding, which are discrete decoding, continuous decoding, and then actually encoding, which is not decoding. Discrete decoding methods use a database and annotations to describe something like a region of interest or a subset of a database in terms of those annotations. Continuous decoding methods try to do the same thing, but with unthresholded statistical maps. For any of you who are familiar with NeuroVault, there's actually an option in NeuroVault when you have a statistical map on there to decode it using Neurosynth. This is the kind of decoding we're talking about when we talk about continuous decoding. And then encoding methods like NeuroQuery take in annotations or text that someone could write and produce a synthesized brain map. Now, I will say that I'm vastly simplifying what NeuroQuery does. It's actually much cooler and much more complicated than just simple encoding, but yeah, I'm not going to get into it in depth. So most of the continuous decoding methods available in NiMARE are just too computationally intensive to actually run for a tutorial. So we'll focus entirely on discrete decoding methods. The two most useful are the brain map decoder and the Neurosynth decoder. So the Neurosynth decoder is just an adaptation of the MKDA chi-squared method that was implemented in Neurosynth, whereas the brain map decoder shares a lot of the methodology, but was developed for brain map and I believe pretty much independently and predates the Neurosynth decoder. I go into detail about these methods in NiMARE's documentation if you want to follow that link. But here's the general idea. First, you have a data set, and that data set has to have both coordinates and annotations. You want it to be a large data set because you're decoding subsets of that data set. So something like Neurosynth or all of BrainMap's database would be good for this. You must select a subset of those studies in that data set according to some criterion. One common criterion is reporting at least one peak in a region of interest or having a specific annotation or label. Then the algorithm compares the frequency of each label within the selected subset of studies against the unselected remainder of studies. And it uses, oh, I'm sorry, that's step 3. It compares the frequency of each label against the frequency of other labels within the selected subset of studies. This is the forward inference analysis, which produces posterior probability, p-value, and z-statistic values, z-statistics. And then in the next analysis, it compares the frequency of each label within the selected data set against the remainder of the database, which is the reverse inference analysis, which produces also posterior probability, p-value, and z-statistic. So for this tutorial, what I'm going to do is I'm going to identify any studies that have the word amygdala in the abstract. Essentially, that's what this search means. And this gives us 38 studies out of the 500 in Neurosynth. Well, the 500 in the subset of Neurosynth that we're using for the tutorial. The decoder then is initialized. In this case, we're not doing any multiple comparisons correction, but we initialize the decoder, we fit it to the data set, and then we transform the based on the subset to the label IDs that we want to look at. This produces a pandas data frame with one column for each of these values up here. That's forward inference, posterior probability, p-value, and z-statistic, and reverse inference, posterior probability, p-value, and z-statistic. And then one row for each label. The same general procedure is performed for the Neurosynth decoder. And I'm just going to run it now, so that way these two will finish together. Well, they'll just run one to the next. So here I've sorted by the reverse inference posterior probability in descending. And as expected, amygdala is the most significant, given that we selected based on amygdala. In the brain map method, we have a bunch of not very interesting labels as the next top several: magnetic resonance, functional magnetic. These could just be noise that we're seeing because it's only the first 500 of roughly 14,000 studies in neurosynth. But after that, we get to emotional, response, neutral, and further down, we would primarily expect to see terms associated with studies that are terms that typically co-occur with the term amygdala in studies, which can give us a sort of a somewhat more quantitative idea of the terms that might be associated with a region of interest rather than the typical literature review. Although, there are major caveats to this. You don't want to make any strong inferences about this. This is really a very noisy procedure, but it can be useful. With the neurosynth decoder, we also see amygdala as number one, and then amygdala response, amygdala hippocampus, reinforcement, neutral faces, threat, etc. Things that you commonly see in papers that talk about the amygdala. All right. So that covers what I wanted to talk about with functional decoding. There's a lot more you can do with it, but most of it is computationally too intensive for a tutorial. We have a fair amount of documentation on it in the NiMARE, on the NiMARE documentation site, though. So if you want to check that out, though, feel free. And to close up, I wanted to talk about NiMARE and the Neurostore ecosystem. So this NiMARE fits into this developing ecosystem of tools for neuroimaging meta-analyses. At the heart of that ecosystem is Neurostore, which is a database containing maps drawn from NeuroVault, images drawn, or coordinates drawn from NeuroQuery, as well as the original Neurosynth database, and from manual additions by users. This Neurostore database uses NiMADs as its sort of data representation that people can export and use. And there's an online tool called Neurosynth 2.0, or at the moment Neurosynth Compose, that is also under active development, that will allow people to select studies in Neurostore, annotate those studies, and perform meta-analyses on those studies, or on their study sets. And that's where NiMARE comes in, because it performs the actual meta-analyses. Then when the meta-analysis is done, it gets fed back into Neurostore and NeuroVault as statistical maps associated with the meta-analysis. If you'd like to try out the new service, there is a link right here. Feel free to sign up. It's currently under active development, so there are bugs and missing features for sure. However, we welcome feedback and future requests. There's a feedback button on the website. So this is the website right now. There is a feedback button where people can provide feedback, which goes to the devs. And it has already populated studies from Neurosynth, NeuroQuery, and NeuroVault, which people can then select and annotate in study sets. This is one that I created a little while ago. Identified 7 studies that refer to pain in the NeuroVault database with statistical maps. Actually, only 6 of them refer to pain. And each of them has statistical maps associated with it. So we'll see this study has PPI analyses, that's psychophysiological interaction analyses, as well as a number of other analyses. And they can be selected within the study set to perform a meta-analysis based on that study set. Then you download the config file and run it with NiMARE locally. And that's the general idea for that. So I don't know when we're supposed to finish up, but
You've got until 5.
Okay.
So you've got another 20 minutes or so.
Awesome. So there is an exercise that I left in case there was time. for those of you who are able to run the notebook. The idea here is to perform a meta-analytic connectivity modeling or co-activation modeling analysis, and then decode the ROI used for that MACM analysis. There is an amygdala ROI mask that's located in the data directory. It's the right amygdala, so here it is. And so the idea is to use the dataset classes get studies by mask method to identify studies with at least one coordinate in that ROI, create a reduced version of the dataset that only includes studies only includes the selected studies above, run a MKDA density meta-analysis on those studies without multiple comparisons correction, because that would take a little while. And then also initialize, fit, and transform a neurosense decoder using those selected studies. So I don't know what folks would prefer. I can just start typing it out or give folks a chance to try and ask questions about it. Yeah, I don't know what other tutorials have gone for in terms of approach here.
So I think it's up to you, but if people want to go ahead and give it a try first, we can maybe open it up to questions for a minute.
Cool.
And I actually have a question, which is a bit of a follow-up question on one of the earlier questions. But this is a really cool tool, and I'm someone who works mostly with surface-based analyses. And so I'm wondering if you would talk a little bit about surface-based analyses like FS average and FSLR, and if there's any intention of adapting this to those kinds of analyses.
That's a really great question. So if in terms of image-based meta-analyses, I think applying these methods to a set of SIFTY or GIFTY files should be totally feasible. I'm not really familiar with surface-based with surface data, so I don't know how results are typically reported. Are they reported in M&I coordinates, stereotactic space coordinates, or?
Typically for surface, you have your own set of coordinates that are related to the inflated cortical sphere. Yeah, the other tricky thing I could see with this is that in surface-based analyses, a particular vertex is not related in space to the vertices around it. So if you use convolutions, you need to re-implement that for a mesh or something.
That's a really great point. Yeah, I don't know that any coordinate, I don't know for sure. I don't know that any coordinate-based algorithms have actually been adjusted or developed for surface-based meta-analyses. So I'm not sure if it's actually been done at all. I could just be missing a part of the literature. But
yeah, to be honest, that wouldn't surprise me, but maybe this is something we should talk about offline sometime.
Yeah, that sounds great. That would be a great
I'd be interested in I'd be interested in talking about those methods. Yeah. Are there any other questions from the in-person people here? Looks like they're all diligently trying the exercise, so.
Yeah. Oh, cool.
So you probably can't see us very well through the camera, but I'm seeing some people who look like they maybe have finished and some who look a little confused. So maybe you can start walking through some of the cells.
Sure. Yeah. I definitely can't see. It's a very tiny window. All right. So I'm going to start with the neurosynth data set. And the ROI file already. So we can use the get studies by mask method on the ROI file, which is it's a data set method. So you just use the data set object dot get studies by mask, and then the ROI file that gets us a list of identifiers, study identifiers, which then I'm printing the length of them just to see how many studies there are. There's 26. So ROI dset is just the sliced version of the overall data set using only those studies. And here we have our 26 experiments in the ROI dset. All right. So we can initialize an MKDA density meta-analysis estimator with, I'm just going to use the default settings. And then we get our results by fitting that initialized estimator to the ROI data set. And the resulting maps are, should use pretty print, but we end up getting a stat map and a Z map from that meta-analysis. And because it's not multiple comparisons corrected, meaning we didn't apply a corrector to it, it took, and we get a P map. It took very little time because really the core meta-analysis step is very simple and fast, especially on a data set of only 26 studies. I'll do the neurosynth decoder. No correction. We fit the decoder to the overall neurosynth data set. And then we want to get a data frame. So this is just a table from it by transforming based on just the IDs like that. And here we go. So this is just searching, this produces the data frame with the p-values, z-values, and probability values for both forward and reverse inference analyses. And it's just sorted alphabetically, so we might want to do sort values by z-reverse, so the reverse inference z-statistic, for example. And we probably want it in descending order so that higher values appear higher in the data frame. And there we go. So when we use the ROI, rather than terms, just the ROI image, the first term that comes up in terms of the Z value for the reverse inference meta-analysis is amygdala. And then fear, conditioning, reinforcement, lots of things associated with the amygdala across the literature. And this is, I neglected to actually plot the results. And so when I plot the actual Z map from the MKDA meta-analysis, it looks a lot like, well, it's probably equivalent to the prepared figure I have here. And I sorted by Z reverse rather than prob reverse, unfortunately. So this is slightly different, but it's fairly similar. So those are two outputs that you get from both MACM and functional decoding. Right. Did anyone have any questions about that or anything else you'd like to know about NiMARE? Or meta-analyses in general, I guess.
I guess I have one more question, which is maybe not a very well formed. I'm curious if there are methods in NiMARE to handle, for example, maps. Like if you had a map in the visual cortex that you wanted to look at across a lot of studies, where you have very nice parameterization of the map in general, not just a contrast parameterization. Is that the kind of thing that NiMARE has tools to handle?
Could you explain a bit more about what you mean by map versus like a statistical image?
So for example, in visual cortex and primary visual cortex, you have maps that are characterized not just by their location, but by the sort of distribution of visual response across the map, the tuning to like particular parts of the visual field. So there's like another dimension of information to be compared there. So I'm wondering if there's anything in NiMARE that can handle that kind of comparison.
So in that case, I mean, so I don't do visual experiments or what's it called, PFRs, PRF, population receptive field analyses. And I'm not really aware of a lot of available data on, say, like NeuroVault for them, but I would assume that they would be provided in sort of like nifty files with a 4-dimensional nifty files where each volume corresponds to a given direction. Is that right? Or a given sort of a value?
Yeah, essentially you'd have volumes that correspond to coordinates like X and Y in the visual field, probably.
Gotcha. So in that case, I mean, you'd have to have enough data out there to actually do the meta-analysis, which, I mean, I guess if you contacted people directly and they were willing to share, that's a possibility. So yeah, in that case, I think you would probably need to do a standard image-based meta-analysis on each of the volumes separately, basically by splitting up the 4D image into a series of 3D images and then comparing the X to the X from a bunch of studies. I don't know if that's the kind of inference that the meta-analytic inference that you'd care about though, with that kind of data.
No, that makes sense. Yeah, thanks.
Go
ahead.
I was just going to say that so I also contribute to BIDS, the brain imaging data structure, and we are always looking for ways to improve how NiMARE both would ingest and output BIDS-like results. So if there was a BIDS-like storage or naming convention and storage organization for those kinds of data, then it would be much easier for NiMARE for us to develop a way in NiMARE to ingest that kind of data and automatically analyze it.
When someone comes up with a BIDS representation for that, I'll let you know. Do we have any other questions in the room here? Or anyone on Zoom would like to jump in and ask a question? Yeah, here we have a question.
Hi, Taylor. I'm wondering if you usually pre-register your meta-analyses, or if that's even something you have to do. Like, is it more data-driven, or what's the best practices there? Or I guess just for someone who's never done a meta-analysis, any other best practices consideration?
Yeah, so Dr. Laird, who presented, who gave a talk yesterday, she is my advisor, soon to be ex-advisor because I've defended already and I'm leaving the lab soon, but she has worked a lot on templates for analysis plans for meta-analyses within the lab that I think would be wonderful to sort of popularize. So in terms of pre-registration, I think pre-registration can be great, especially if you do something like a registered report where you can actually get peer review, feedback on the analysis plan before you implement it. I think developing an analysis plan and especially having an idea of what the inclusion and exclusion criteria should be is a, if not necessary, then at least highly recommended step for performing a publication level, proper like meta-analysis. I would say that doing large scale sort of cobbled together meta-analyses with something like Neurosynth, these can be useful. For example, if you want to define regions of a priori regions of interest for a first order fMRI study later on, they are not on their own sufficient for a publication. So, I would recommend against, say, just searching pain in Neurosynth and then saying, let's write this up. A number of times people do something more advanced with that kind of large scale database, like meta-analytic independent components analysis or meta-analytic clustering, where you try to parcelate, where you try to segregate studies into different groups or parcelate regions of interest. That's where that can be useful. In terms of an actual, just a regular meta-analysis, manual curation based on predefined inclusion exclusion criteria is definitely the way to go.
Great. Any other questions?
Maybe to follow up on this one, Taylor, since you've been like in Angie's lab for a while, do you have a sense of how much p-hacking is happening on the meta-analysis world? I think that whether you really should consider pre-registration or not is really a function of how much p-hacking is going on, right?
Yeah. So I would say in terms of the actual data sets, like which studies are actually included, I've never really encountered people saying, we didn't get results, let's find some more studies and look harder and harder. They typically do a comprehensive search at the beginning. The area where I think there's a strong potential for p-hacking is thresholding. The same with fMRI, or with your first order analyses, defining different voxel level and cluster level thresholds of significance, I think is something people have to fight against, hopefully by setting those levels in a principled manner ahead of time. I don't know, there may be other ways people can p-hack with meta-analyses, but that's really what comes to mind for me.
Great. Any more questions? Okay, well, we're about at time, so let's thank Taylor for the great talk. And that is it for our curriculum today. So thank you everyone for joining us. We'll see you all here tomorrow. Feel free to hang out for a while. Yeah, let's thank Taylor again.
Yeah, thank you. It's a wonderful time. And hope you all use NiMARE, find it useful.